Hello and welcome to this video in the wave series. Today we're going to look at transverse and longitudinal waves. We're going to get a definition for each one. We are going to look at how they both travel. We're going to compare between them, looking at the similarities and differences. And then we're going to look at some examples of each one. So, as always, I'm going to start with a recall task in order to check your previous learning. So as soon as that screen appears, I'd like you to pause it, attempt the questions, and then check your answers, and then you'll be ready for the new learning. So let's start to build our definition of a longitudinal and a transverse wave. So from the very first video, you should remember that all waves transfer energy from one place to another. So we've got point A and we've got point B, and any wave will take energy from A to B. And so that red line we're just going to label as energy. Now, in order for a wave to be propagated is a very fancy term for meaning created. So in order to create a wave, you have to move something in a forwards and backwards direction. And we had a term for that. We called that oscillate. And you can oscillate something up and down. So that's a forwards and backwards direction. So up, down, up, down. But you can also oscillate something left, right, left, right. So there are two different ways to oscillate. And it's the combination with the direction of the oscillation and the direction of the energy transfer that inform us whether something is a transverse or whether it is a longitudinal wave. Let's have an example. Let's say we've got a person. So we'll draw a person here. And this person has got hold of a slinky. So one of those springs that you put on your stair steps, and they move down with each other. So there's the spring. So this person is person A. I'm going to write person A on their hat. Let's give him a nose and an eye so we can see what he's doing. Now, they are going to transfer some information from point A. And in point B, we've seen this example before. There's going to be another person holding this slinky, and they are, let's have a different type of hat. There we go. They're person B. Oh, they haven't got a nose. There we go. So also they've got a tiny head, but that'll be fine. So person A is going to transfer the information from A to B. So the energy is going to go here. So energy is going to be transferred from A to B. Now there are two ways that person A could transfer that energy. They could oscillate their spring up and down, or they can oscillate it back and forth, left to right. So let's start with the first one. Let's say that they're going to oscillate their spring up and down. So they're going to move this spring first off up, and then they're going to move down. Now if they did that, we would see a wave formed in the spring, and it would look like this. Now we've seen this type of wave before. Let's draw it here. So we have got this line here, which is shown as which way the energy is going. I'll keep that in red. So the energy is going from A to B. And we've got, remember this line represents the line of zero disturbance. And then we've got a positive displacement and a negative displacement. So we've got our wave, which is going like this. And this is the type of wave we get when we oscillate up and down. Now, I want to have a look at the peaks and the troughs. So I'm going to draw in the displacement of the spring, so that at this point the spring had moved up. At this point the spring had moved down, up, down, and up. And that's what's made our wave pattern. Now, it's not the same part of the spring that's moving up and down. That's what the wave is doing. The wave is making it move along. But so this part of the spring went up, a different part of the spring went up, a different part of the spring went up, a different part of the spring went down. So the individual particle actually only goes up and down, and it stays. You see, it's a perfectly straight line. Now, if I draw the same diagram, but this time, I'm not going to show the waves. I'm just going to show the positions of the spring. So we've got that one like that one like that, and so on. There we go. Now, what we can see now is the energy is moving that way, but the oscillations are moving in a totally different direction. In fact, if we look here, there is an angle between them, and we should know that that type of angle there is a right angle. And a right angle is 90 degrees. So we can actually now come up with our definition. And we'll write it here. And this is a transverse wave. So our definition is, in a transverse wave, the oscillations, that's the movement of the spring, are at, no, we already got this angle, they're at 90 degrees, it's a right angle, to the direction that the energy is going. Okay, I'm going to read that again because it's such a really, really important definition. In a transverse wave, the oscillations are at 90 degrees to the direction of energy transfer. I'm going to underline oscillations, and I'm going to underline 90 degrees and energy transfer. Now, there is another term that you might see. So instead of saying right angle or 90 degrees, you might see this term, perpendicular, and that just means the same thing. It means at a right angle. So you might see a transverse wave, the oscillations are perpendicular to the direction of energy transfer. But hopefully that should explain what a transverse wave is. Okay, so how else could our person A get the energy in the spring to go to person B? Well, we've looked at an oscillation up and down, and we said that that produces a transverse wave. So they could do the other type of oscillation. They could move the spring forwards and backwards, like this. So if they were to get their spring to move forwards and backwards, again, that would create a wave that would move along the spring and would transfer energy to person B. But the wave wouldn't look like that up and down shape that we got with the transverse wave. It would look very different. I'm going to try and illustrate it for you now. So what would happen is, when person A moved the spring forwards, parts of the spring would be pushed together. So we would get the spring that was like that, where the parts have been pushed really close together. I'm just going to draw a couple of those in. So these are the bits where the spring has been pushed close together. So the forward movements. And then when person A brought the spring backwards, the spring would actually get stretched, so that the parts of the spring would be stretched further away from each other. So we would get a wave there which was really stretched out. And again, a wave that is really stretched out. Let's try and join it to there. And again, stretched out. So we see we've got this sort of shape now, where we've got the waves which are moving forwards and backwards, but stretched out. Okay, so let's draw that wave. So again, that's terrible. We need a ruler. Again, the energy is going from this position of zero disturbance. So that's the energy. It's going from A to B. But this time, we're just going to draw in the wave fronts. So we've got some places where the waves are very close together, and some places, so let's draw the close together ones. And we've got some places where the waves are very much spread out, so let's put those in as well. And this is the shape of the wave that we get. And remember, these waves actually are going forwards and backwards. Now we said that the type of wave depends on the way that it's oscillating compared to the energy transfer. In the transverse wave, the oscillations were at right angles. In this type of wave, this is the longitudinal wave, the oscillations are actually going in the same direction as the energy transfer. So we say that they are parallel. So let's bring a definition for this type of wave. And we'll write it here. So in a longitudinal wave, the oscillations are parallel, so in the same direction to the direction of energy transfer. I'll read that one more time. So in a longitudinal wave, the oscillations, so the backwards and forwards movements, are parallel, so in the same direction, to the direction of energy transfer. So now we know what a transverse and longitudinal wave are, we should look at the similarities and differences between them. So what I've done is I've divided my board into two sides. On this side, we've got a drawing of a frozen wave diagram from a transverse wave. And on this side, we've got a frozen wave diagram from a longitudinal wave. So we can start to label this. Now, we've done this one before, so we can rush through this one. This very bottom of the wave here on the transverse wave is called a trough. And the very top part is called a peak. Okay. We can also identify the amplitude. So that's the area, sorry, the distance from the line of zero disturbance to the maximum displacement. And that can happen in both positive and negative displacements. So that is the amplitude. And the other thing that we can find on here is the wavelength. So the wavelength, as we've looked at in a previous video, is the distance in meters between two equivalent points. So we could go peak to peak, or we could go trough to trough, or we could go equivalent position on the line of zero disturbance. So here to the next equivalent position to here. So we could say between there and there. Now, to make this easier for you to see, I'll just bring this down underneath. So we've got from this position here to this next position here. So that distance is one wavelength. So let's look at our longitudinal wave and let's see how it's different, but also how it's similar. So again, we've got areas of we've got this energy traveling in the same direction. So we can say that both of them transfer energy. Now, we haven't got peaks and troughs in this one. What we've got is we've got some areas where the waves are closer together. And we call these areas where the waves are squashed together, we call them compressions. So that is a compression. And the areas that are spread out, so that's where the waves are stretched. This area is called a rare fraction. So rare fractions are the areas where the wave is spread out, and compressions are the areas where the wave is squashed together. Now, in the last video, in the last transverse wave, we saw that we had amplitudes. That was the intensity of the wave. So, for instance, if it was a light wave, like a transverse light wave, then the intensity of the wave would be the brightness. So, a really bright light would have a very high amplitude, and a very dim light would have a very low amplitude. In a longitudinal wave, such as sound, we can have amplitude as well, because we can have very quiet sounds and we can have very loud sounds. So that would look like this. So if I wanted to make this sound quieter, it's just a decrease the distance of the distance of the wave from the zero point of zero disturbance. So decrease the height of the wave, and then it could be, this sound could be a louder sound here. So we could make this bigger. So again, the amplitude, the intensity, is just represented by the distance of the from the line of zero disturbance to the peak of the wave, often the maximum distance between the zero disturbance to the top. So we still have an amplitude, and we also still have the wavelength. Now, again, it's exactly the same definition. It's from two equivalent points, the distance between two equivalent points. Now, on here, we could say from the middle of a refraction to another refraction, so here to here. Or the best one to use is from the center of a compression to the center of the next compression. So from here to here. Again, that could be difficult to see, so I'll bring it down below. So we've got from this line, and it's going to the middle there. So again, that's the wavelength. So far the similarities: both transfer energy, both have a wavelength, both have amplitude. Differences: this one has the transverse has peaks and troughs, whereas the longitudinal has areas of compression and refraction. An absolutely key skill and really common exam question is to ask you to be able to compare between the properties of transverse and longitudinal waves. Now, when you are going to answer a question like that, you need to try and organize your ideas before you go ahead and try and answer it, because otherwise it might all be a bit of a jumble, and it won't be easy for the marker to pick out the points that you're trying to make. So a good way to do that is some kind of graphic organizer. Now, the graphic organizer I've chosen for and use for every single type of comparative question is a Venn diagram, because it just does an absolutely fantastic job of organizing our ideas. The Venn diagram is two circles. Everything in this circle are properties that are specific to transverse waves. Now, you might notice I've written transverse above it, but I've also drawn a diagram because the word transverse is quite an abstract word. Whereas this drawing here, if you can remember that, you can actually prompt yourself to know a lot about transverse waves. And the same with longitudinal. So if you can just try and remember the drawings rather than the definitions, that will, that will really help you out. So let's start with something that is the same. So this middle section on the graphic organizer, on the Venn diagram, is properties that are the same for both transverse and longitudinal waves. So something that they both do. Well, one thing that they both do is that they both transfer energy. So let's write that in here. So they both transfer energy. So if I was to start to write my answer, this might be a great place to start. I could say a similarity between transverse and longitudinal waves is that they both transfer energy from one place to another. Great. But it's not a full comparison yet because I don't have any ways that they're different. So let's add in some ways that they're different. So this diagram is useful here because we can start to think, well, these diagrams are different. How are they different? Well, this one has got peaks and troughs. So let's write that in here. So has peaks and troughs. Okay. Well, that has peaks and troughs. Now, your idea, the idea when you're writing a comparison is to be comparative. Use comparative sentences. So you should be saying like a sentence structure like, they are both the same, they both do this. However, a difference is one does this and the other does this. So if this one has peaks and troughs, what's the opposite? Well, this one has areas of compressions and refractions. So we could write that in here. Has areas of compressions and refractions. Okay, so what I'm going to do is I'm going to pop up a much more professionally drawn one of these, and I'm going to put on all the different properties that we've talked about in the video so far. And your job will be to draw your own Venn diagram, just a sketch like mine, and to sort those properties into things that are specific to transverse, things that are specific to longitudinal, and things that are similar between both of them. What I'll do before I do that though is I'll just talk you through how our answer would sound so far and why this graphic organizer is so powerful. So far, just with the points that we've made, we could say a similarity between transverse and longitudinal waves is that they both transfer energy from one place to another. However, a difference is transverse waves have peaks and troughs, whereas longitudinal waves have areas of compressions and refractions. So far, with just these 3 points, we have picked up 3 points from what would probably be a 6-mark question. Okay, I'll let you have a go and see if you can do the rest. In the last part of this video, we are just going to look at some examples of each of these types of waves. So an example of a transverse wave is a water wave. Now, for instance, if you get a tank of water and you get an object and you oscillate the object in this tank of water, you will generate some ripples on the surface of that water, which will produce a wave like that. Now, you only see, for instance, if you're stood here, let's say you're stood and this is the beach, and you're stood looking that way, you would only see the tops of the waves. So that might be the view that you would most likely be used to. There's the tops, but there is also something underneath as well, because remember, waves oscillate forwards and backwards, so there is an area of zero displacement, and there is a positive direction and a negative displacement. Another type of transverse wave is, well, in fact, a group is all of the EM waves. Now, EM is shorthand for electromagnetic waves. And electromagnetic waves, we are going to have a whole video dedicated to that. But I'll give you 2 examples now. So, light. Light is a type of EM wave. So the sun, okay, gives out loads and loads of waves, but one of the waves that it gives out is light. So you stood here on planet Earth, you can see the sun. And the reason you can see the sun is because the light from the Earth travels and you detect it with your eyes. So that is another type of transverse wave. Another EM wave, we'll have a look at another one, radio. Right, these waves are absolutely everywhere all around us. So there's some kind of broadcast in place and they'll have a big antenna on the top. And the antenna will generate a wave, and that wave will be sent out. Actually, the wavelength of radio waves are much longer than light waves, so I don't want that misconception in there. So like that. And your radio would pick it up with its receiver, and you would hear the sound that was broadcast by the radio station, another type of transverse wave. And the last one that we need to be aware of are an earthquake wave. Now, an earthquake, in fact, is made up of 2 waves. You get primary waves and you get secondary waves. And the transverse one is the secondary. Now, the way I remember this is because if we think of a transverse wave of looking like that, if we were to turn that round, you would get that, okay? So if we were to turn it and rotate it, we get that, and that looks like an S. So that helps me remember secondary. Now the secondary wave, so basically you have the Earth here, and the waves are sent through the Earth. So that's the medium, is the Earth, and it shakes a building. And you can either shake that building up and down or side to side. Now the secondary ones are the waves that are going to be sent out like this. So they are going to move the building side to side. So these are the ones that are going to do a lot of damage. Earthquake. So yeah, they are the dangerous earthquake waves. So in longitudinal, an example would be, and the most famous example is sound. So when you speak, your voice box in here vibrates, and then this vibrates some particles here, and you give out a longitudinal wave that can then be detected by someone else. And it's a wave, it travels forward and backwards. You can hear it if you, you can feel it if you put your hand on your throat. You can feel the vibrations that are causing the oscillations that are causing this wave, and it's just a particle hits another particle, and then that sound spreads out. Another one, ultrasound. Obviously, it's another type of sound of a different frequency. Now, ultrasounds, you might mostly be familiar with. They're used for scanning. For instance, you could put an ultrasound detector, and you can send a reflection, and that can bounce back up, and you can detect things. And from these detections, you can make measurements and you can make images. So a really common one as an ultrasound is to look at babies inside of their mother's stomachs, and you can see an image of the baby using the ultrasound. Or you might want to use the same thing to look at how far something is underneath the sea. All right, you don't want to go down there yourself. You get an ultrasound detector, you send the sound wave down, and it gets reflected back up, and you can use those measurements in order to figure out how far the object is underneath the surface. And the last one is the primary earthquake wave. Now, this one, again, exactly the same thing. Some waves are transmitted through the Earth's surface. Here's your building. Now, in this way, the waves are just going to go up and down. So that building, even though this is still going to shake the foundations of the building, it's moving it up and down, so it's not actually moving it side to side. So this one is not quite as dangerous. Okay, they are our types of waves. What I'm going to do now is I'm going to put some questions up on the video that are summary questions of everything that we've learned on this topic. I'd like you to pause the video. I'd like you to take your time to answer those questions, and then you can check your answers when you restart the timer again. Okay, thank you for watching.